Hello and welcome to Database Management Systems. I'm Jovita Christie, and in this video, I'm going to give you an introduction to relational database design. So let's begin. First, we are going to see what the different goals of relational database design are. The first goal is to generate a set of relation schemas. So whenever you have to design a database, you need to first of all decide what types of relations you require, how many relations you require, and also decide what will be the columns in those relations, the attributes, and the data types of these attributes. These are some of the basic necessities while designing a database. And it's not as simple as it sounds, because to design a database, you need to make sure that it is efficient. Efficient when you perform insertions, updations, deletions, or just when you simply want to view the tables, when you want to view your data. So in order to make sure that your design is efficient, you need to study relational database design very thoroughly. And one of the goals of relational database design is definitely generating a set of relation schemas. The second goal is definitely storing data, because you have created a database, and the sole purpose of a database is to store data and then, of course, view it. So the next goal is to reduce unnecessary redundancy. Now, what is redundancy? Redundancy means duplication of data. So when you have the same data occurring again and again for no reason, for example, maybe you are creating a database for students in your class, and you decided to store everything in one table, and then you realized that you're trying to store different subjects that the student is studying. Now, because you're storing all the data in one table, and there are at least 5 subjects that each student is studying, you would have to store the data of that student several times. So that means repeating the address of the student, repeating the phone numbers, email IDs, everything. And this is unnecessary, because you can create a design that is more efficient than that. So you can learn to do this. You can learn to remove this unnecessary duplication or redundancy by studying relational database design. And the last goal is to retrieve information easily. The purpose of database is not just to store data, but also to fetch data and to be able to view that data. And to do that, it's necessary that once you ask for some data, it doesn't take a very long time. Because if it's going to take, say, about an hour for you to get your data, then that's not an efficient system. So relational database design also allows you to retrieve information easily. Now, whenever we talk about relational database design, the concept of atomic and non-atomic domains comes up. And this is a concept that I've already talked about in relational models, which I explained in my previous videos. But I'm just going to revise it once again, because it's important even in studying relational database design. So what is an atomic domain? A domain is atomic if elements of the domain are considered to be indivisible units. And that means you have a column, and whatever values you're storing in that column must be indivisible. And you'll come to know what that is when I give you some examples here. So consider that you have a table called employees, where you are trying to store an attribute called children. Now, consider how that's going to work out. For one employee, you're trying to store the names of that employee's children. So an employee could have one child, some employee could have two children, and another employee could have three children. So in this case, how are you going to store this data in your database? Are you going to store each employee with all the details thrice because the employee has three children and you want to store all three children in separate rows? That is one possibility, but there's a problem with that, and you'll come to know about this type of a problem as we proceed in relational database design in the upcoming videos. Now, the second possibility is, of course, storing everything in one row and putting all three children by comma separated values in a single row, single column. And that's possible. However, this also could lead to problems in your design. And this too, you're going to study in the upcoming videos. Let's take another example of a non-atomic domain. So consider that you have an attribute called address, which can be divided into city, zip code, area code, and house number. Now, because the address can be divided into so many different parts, you can say that it is not indivisible, it is divisible, because you could always store all these things in separate columns instead of storing them all together in under the address column. And you could also create a separate table to store just the address with all these separate columns. So this is again a non-atomic domain, and the other non-atomic domain we saw was children. So those are all non-atomic domains. Atomic domains would be somewhere you can store only one value. For example, an ID of a person, you're going to store only one value there. Name of a person, that could be an atomic domain. So all these are atomic domains, and children and address are non-atomic domains. And we're going to make extensive use of this concept when we study normalization in the upcoming videos. Now let's take a look at what functional dependencies are. These are also very useful thing in database design. So what is a functional dependency? It is a many-to-one relationship from one set of attributes to another within a given relation. So when we talk about functional dependencies, we're talking about relation between one column of the table with another column of the table. And usually in ER models, when we construct relationships, we construct them between one table and another. We never construct relationships between one column of a table and another column of the same table. However, functional dependency deals with a relationship between one column of a table and another one, and it is a many-to-one relationship. You'll get to know more about this with different types of dependencies and examples that I'm going to present now. First of all, take a look at this table right here. This table contains 4 columns: S hash, city, P hash, and quantity. And S hash stands for the supplier number. This is a very small sample table taken from a database for auto parts supply. So S hash is the supplier number. City is where the supplier is located. P hash is the part number that the supplier is selling, and quantity is the amount or the number of parts of that type sold by the supplier. So you'll notice here that there are several suppliers, S1, 2, 3, and 4, based in different cities and selling different types of parts and different quantities of those parts. Now here we are going to try to identify functional dependencies by checking if one column is having a many-to-one relationship with another column of this table. So the first type of functional dependency that I'm going to talk about is a trivial functional dependency. A trivial functional dependency is something that is existing, but it's not something that affects the table. Functional dependencies in general are bad for your database design. The fewer functional dependencies you can have for each table, the better it is for your database. And that's why we try to reduce functional dependencies. But a trivial functional dependency is a dependency that does not matter. So even if it's present, you don't have to worry about it. Now, functional dependencies are written in this manner. You have the left side of the arrow, as you can see, and you have the right side of the arrow. And we read it as S hash P hash determines S hash. So that is how this thing works. Now, if you look at the table, this is something very simple to understand, that if you take any pair of S hash and P hash, it is going to give you a unique value of S hash. For example, if I take S1 and P1, then for S1 and P1, the supplier is S1, and that's so easy to tell. If I ask you a question for a combination of S hash and P hash, who is the for a combination of S1 and P1, who is the supplier? Your answer will be S1. So it's even the question itself sounds absurd because I'm already giving you the answer and then asking you a question. So that's why this is a dependency that does not matter. The next type of dependency we're going to see is a non-trivial functional dependency, and that you can see here, S hash determines city. So if I ask you a question, where is supplier S1 located? You will answer that it's located in London, because you can see that S1 is appearing twice in this relation, and both the times it appears with the city London. Now, if I ask you where is S2 located, you'll answer it's Paris, because both the times that S2 comes in this table, it comes with Paris. And if I ask you where is S3 located, you'll once again answer it's located in Paris, because it appears once in the table with Paris. And if I ask you where is S4 located, once again, you can give me one answer, which is London, because it appears thrice in the table and all three times with London. This is a non-trivial functional dependency, and this is something to take care of. You would try to remove this type of dependency from your table by using a technique called normalization, which we are going to see in upcoming videos. Now, what you have here is a functional dependency, because when I ask you a question about S hash, you are able to give me one answer. If suppose S1 was located not just in London but also in Paris, then this dependency would not exist. This exists only because S1 is only located in London, S2 only in Paris, S3 only in Paris, and S4 only in London. So it's a many-to-one relationship from S hash to city. Take a look at this dependency, which is a time-dependent functional dependency. S hash determines quantity. So you'll notice that whatever was happening with S hash and city, same thing is happening with S hash and quantity. Every supplier is supplying the same quantity. For example, S1 is supplying 100 every time, no matter which part it is. And S2 is supplying 200, even though it is selling two different parts, P1 and P2. S3 is supplying 300, and S4 is supplying three different parts and all three with 400 quantity. So this type of dependency is time dependent because it exists at the moment. It's not necessary that it's going to stay forever. It's possible that if you open this table after about an hour, you might find that S4 has now sold 500 parts of P5 because uh, because the quantity changed. And now this dependency no longer exists because the many-to-one relationship is not satisfied for S4. So it is time dependent, and most of the time it will take care of itself, and you don't have to worry about this type of a dependency. Take a look at this dependency, which is time independent, which is about S hash P hash determines city. If you take any combination of S hash and P hash and find out where the city is, it's going to be one unique city. So it's a many-to-one relationship. And it is time independent because the supplier is not very likely to change the location within an hour, like the quantity changes. And so it is time independent. That's it for this video. I'll see you in the next one. Thank you for watching.